Hello students, today we are going to solve a question from CSIR NET 2023 June. Question ID is 705069 and this is basically from molecular physics. The question is given that you have two different molecule H2 and D2 molecule. Both shows pure rotational spectra. So basically you have to calculate the ratio of frequency separation between first Stokes line and first anti-Stokes line for H2 molecule to that of D2 molecule. That ratio you have to calculate. Okay, so if you see the structure of H2 molecule, it can be think like you have a on H on. Okay, and for D2 molecule, we can think like on H2 on H2. Okay, if m is mh is the mass of a hydrogen atom, then mass of a deuterium can be written as 2 times mass of a hydrogen. Okay, so as in the question what they have asked, we have to calculate that frequency separation between first Stokes line to that of anti-Stokes line for a hydrogen atom to that of same separation for D2 atom. That ratio we have to calculate. Now if you see that concept of rotational Raman spectra, that you have a H2 molecule, its spin is half. So basically it's a fermion. Okay, the fermion, and for fermion system, that all J levels are present. All J levels are present, but J equals to odd levels, for example, on 3, 5 is more populated. Okay, more populated as compared to J equal to even state. So obviously, when there is a transition from odd to odd, you'll get more intense line. But all J levels are present, it means you'll get all rotational Raman lines. But that odd to odd state transition, for example, J equals to 1 to 3 transition or 3 to 5 transition, that will be more intense as compared to even transition. On the other hand, you have a D2 molecule. If you see that spin of D2 molecule, say on, it means basically boson. And for bosonic system, again, all J states are present. States are present. But for bosonic system, that J equals to even, for example, 0 to 4, they are actually more populated. So obviously that even to even transition is more intense. For example, if you see that J equals to 0 to 2 transition or 2 to 4 transition, this will be more intense. But if you summarize that all J states are present, so there will be no missing of Stokes and anti-Stokes line. But obviously, that odd to odd transition will have more intense for H2 molecule, and for here for D2 molecules, a bosonic system, for this molecule, that even to even transition, that lines will be more intense. But all lines will be present. Okay. Now if you see that frequency shift or wave number shift, they are actually same meaning, because frequency is proportional to wave number. 1 by lambda, both are actually inversely proportional to 1 by lambda. For Stokes line, For Stokes line, you can represent that frequency shift delta nu, that can be written as minus 4b j plus 3 by 2, where j can take values 0, 1, 2, and so on. J equals to 0 will be the first Stokes line, and for anti-Stokes line, that frequency shift will be plus 4b j plus 3 by 2, where j can again take value 0, 1, 2, and so on. Okay, obviously for that first anti-Stokes line corresponds to j equals to 3 by 2. So if you substitute for first Stokes line, if you substitute j equals to 0 here, then you will get that will be minus 6b, because 4b into 3 by 2, that will be 6b. Okay, when j equals to 0, that is giving you first Stokes line. And similarly, j equals to 0 here will give you first anti-Stokes line, and that will give you 6b for j equals to 0. Okay, so obviously if you see that frequency shift between first Stokes line and anti-Stokes line, that will be how much? 6b minus of minus 6b. So that will be 12b. That is well known here. Now I have to calculate that ratio. To calculate that ratio, so delta nu for hydrogen atom divided by delta nu for D2 atom. Not atom here, sorry, it will be molecule. So obviously if you calculate, so this will be corresponds to 2 B1, where the B1 is the rotational constant of this molecule, divided by 12 B2. 12 will be cancelled, so B1 by B2. And you know that B, rotational constant B, is inversely proportional to reduced mass, mu. Okay, so it means it will be mu2 by mu1. Now, if you calculate the reduced mass of hydrogen, so you can write that mu1, this is the reduced mass of hydrogen, that can be written as mh into mh divided by mh plus mh into Na. Okay, and that you can write mh is the mass number. If you write, so it will be on into on divided by 2 Na. So that will be on by twice Na. Okay, here mh means mass of a hydrogen atom, that will be on by Na. So if you apply the concept of Avogadro number, that will be nothing but mass number of this into mass number of this, that is on into on divided by mass number of this, that will be 2 times 1 by 2 times Na. Similarly, mu2 you can write 2 into mh into 2 into mh, because mass of a deuterium is nothing but 2 times mass of a hydrogen, divided by 4 mh into Na. And you know mh is nothing but on here. If you substitute, you will get basically on by Na. So now if you substitute that ratio here, so mu2 is nothing but on by Na divided by on by twice of Na. So Na will be cancelled, you will get this ratio, that will be 2. So the ratio of this frequency shift or frequency separation between first Stokes and anti-Stokes line for H2 molecule to that of D2 molecule, that will be 2 here. So this will be the correct answer. Thank you.